Hello. So in this lecture, I'm going to spend some time talking about the vector potential, its fundamental properties, and how to derive the vector potential for a certain current configuration. So the reason why the vector potential, the notion of the vector potential is called for in magnetostatics is this fundamental relation saying that the divergence of the magnetic field is zero. And as you know, this relation is not just confined to the magnetostatics. In fact, this relation holds for all situations in electromagnetism, including the situations where the most violent kind of temporal fluctuations of the magnetic fields are involved. So this is an absolutely valid relation. And you can think of it as a mathematical identity. And what this identity is telling us in return is that it's always possible, under all circumstances, to express the magnetic field as the curl of some other vector quantity, which I write down here as A. And A is often called the vector potential. Um, and um, and so from the mathematical standpoint of view, this equation, which is one of the four fundamental equations discovered by Maxwell, can easily be substituted for by this other relation. So this relation looks more like the definition of the vector potential in terms of the magnetic field, or maybe you can call it the definition of the magnetic field in terms of the vector potential. But in either case, this looks to be more of a definition rather than a statement about natural laws. Whereas we tend to think of this divergence-free condition as a statement of the natural law. But in fact, mathematically, they are really saying exactly the same thing. And perhaps this is the reason why one should pay more attention to the vector potential as a physical quantity. Because not only is this a definition of the vector potential, but it's also a statement of the physical law that the divergence of this magnetic field is always zero. Also, this theorem pertains to the fact that we don't have anything like the magnetic monopole in the universe. Okay, so the absence of magnetic monopoles in the universe is in some sense embodied by this relation that the magnetic field is always expressible as the curl of some other vector field. Okay, but in reality, what one ends up measuring is always the magnetic field. I really cannot think of an experiment which directly measures the vector potential. So it makes much more sense to think of the vector potential as coming from the magnetic field. Although at a formal level, I have written, the way this equation is written out, it looks like the magnetic field is defined in terms of some pre-existing vector potential. But in reality, actually, it makes more sense to think of the vector potential as being defined in terms of the magnetic field. Okay, so this is an aspect of this relation which is not very often emphasized in in classes on electromagnetism, but I think that's a kind of regrettable custom that one doesn't emphasize it too much. I personally find this to be a quite important observation. And such observation is also embodied in the following set of equations. So here's an explicit equation which, for instance, tells us exactly how to compute the x component of the vector potential in terms of the integral of the known values of the magnetic field. So here I've used this expression where the integral of the y component of the magnetic field along the z-axis is employed to compute the vector potential along the x-axis. So notice that these indices are kind of crossed. And that's because these relations between vector field, vector potential, and the magnetic fields are through this curl, which tends to mix the components of the vectors involved. Okay, so at first sight, this integral relation doesn't seem to make any sense whatsoever. But in that case, you just have to bear with me and wait for the final verdict on whether this prescription makes any sense. Okay, so the y component of the y component of the vector potential is given by the integral of minus the x component of the magnetic field. And furthermore, we're going to assume that the z component of the vector potential depends only on the z coordinate and not on any other coordinate. And this is despite the fact that the magnetic field itself can be some arbitrary function of both x and y and z. However, even in that situation, it's entirely possible to choose the vector potential in such a way that the z component depends only on the z coordinate and not on the x or the y coordinate. So all of this sounds like magic, but you will see that it's not that magical after all. So first of all, let's try and check whether these prescriptions will give us what we want. And what we want is that by taking the curl of the vector potential, we do recover the magnetic field. So what we have to check is simply whether this curl component of the curl will be able to reproduce the x component of the magnetic field, the bx. But as mentioned earlier, by assumption az is only a function of z coordinate. So therefore, taking the derivative with respect to the y coordinate does not produce anything. It just gives you 0. And there's a second derivative, according to this definition, will nicely give you the bx. Okay, so already we have a strike one as far as achieving our goal is concerned. So let's see what happens to the other component of the curl. And for this, the second expression over here is also 0 because by assumption az is a function that only depends on the z coordinate. So therefore, this derivative will be 0. Now, this first derivative, according to this definition, will be just giving out by. Okay. And finally, the third component, the z component of the curl, is according to these two definitions for ax and ay, will be the integral of this plus that. And these two terms are nothing but the two pieces of the divergence of the magnetic field. Okay. But we know that the divergence of the magnetic field is absolutely equal to 0, which says that the sum of these two components must be equal to the remaining component of the divergence with the minus sign over here. And therefore, this minus sign gets canceled by this minus sign with an overall plus sign. And you have the integral of a derivative. And the end result is, surprisingly, just exactly what we wanted. Okay, so apparently this simple construction is enough. It's enough to be able to allow us to write down these vector potentials in terms of the existing knowledge of the magnetic field. Okay, and in case you missed this, we didn't even have to specify what this AZ function was. Okay, so you might be wondering, why is it possible at all to make this relation work, even when you don't even know exactly how to write down all the components of the vector potential A. And indeed, we did not even have to specify or work out what this AZ function has to look like. And if you look through the derivation, then you see that you didn't have to know what AZ was, because by this divergenceless condition, the sum of the derivatives of the x and y components were equal to the minus the derivative of the z component. Okay, so that's how you were able to get this bz component popping up at the end of the calculation. So what this is telling us is that the different components of the magnetic fields and the different components of the vector potential are pretty closely related, so that if you have enough information about, say, two of its component, then you don't even have to bother to work out what the third component has to be. It's often the case that there is enough constraints in the equations of magnetostatics that the third component is sort of determined in terms of the other two components. Okay, so that's the thing that might be useful to keep in mind about the nature of the magnetic fields and the vector potential fields. Okay, so now moving on, because this magnetic field is expressible as the curl of the vector potential, then its use becomes evident when one tries to compute the magnetic flux by performing the surface integral over some open surface, or even a closed surface, of trying to measure the amount of magnetic flux through that surface. So as usual, you take the inner product of the surface area element ds with the local magnetic field, and then integrate that over the entire surface, and that ends up giving out the magnetic flux through the surface. And now, since magnetic field is the curl of the vector potential, you can invoke the Stokes theorem to express the integral as a line integral rather than a surface integral. and then show that the magnetic flux through the surface is equal to the line integral of the vector potential along the perimeter of that surface. Okay, so this observation, of course, takes place in the context of classical electrodynamics, but also this has huge implications in the quantum mechanics and the behavior of quantum mechanical particles in the presence of magnetic field, as you probably already know rather well. Okay, important aspect of the vector potential is that it's not unique. And what I mean by that is, suppose you have found a vector potential whose curl is precisely equal to the magnetic field you have in mind. However, if you change that vector potential by the amount equal to the gradient of some arbitrarily scalar function chi, then because the curl of the gradient is strictly zero, no matter what is the nature of this function chi, you still obtain the same magnetic field by performing the curl. Okay, so that means no matter how hard you try, it's never possible to find the unique answer to the question of what is the vector potential corresponding to a given magnetic field. And probably the simplest example of that phenomenon is presented by these two choices of the vector potentials, which once you take the curl, will give rise to exactly the same uniform magnetic field along the z direction. And also, when I say that I can construct the vector potential for any given magnetic field configuration through these prescriptions, what I really mean is that this is one possible way to write down the vector potential, which gives the right answer. And there can be infinitely many other different shapes of vector potentials with the same result for the magnetic field. Okay, so when one considers the connection between the vector potential and the magnetic field, one should never forget that there's this many-to-one correspondence between the kind of vector potentials you can have and the magnetic field that you get from taking the curl of the vector potential. Okay, so now with this definition of the vector potential, the other half of the magnetostatics relation becomes double curl, which you can recast in this way using the vector identities. So you have this thing minus this thing equal to the current density, which is obviously a very complicated expression. But then you can use this non-uniqueness of the vector potential to your advantage. So suppose that your initial choice of the vector potential gave you the divergence equal to some non-zero function. Okay, so then instead of sticking with that vector potential, you can try out a different vector potential which differs from the original choice by this gradient of a scalar function. So this new vector potential will satisfy the divergence, which is the original divergence f minus the Laplacian of that scalar function we just introduced. And it's always conceivable to choose this chi function in such a way that this difference becomes 0. Okay, so the f and the chi are just the source term and the potential function in the Poisson equation, and we know how to derive the general solution of the Poisson equation. So so that means that no matter what this f function is, as long as it's not too weird, you can always find these function chi such that its Laplacian equals that very function f. So now you claim that you're going to use this function chi, and instead of adopting your original choice for the vector potential, you're going to use this different choice of the vector potential. And this different choice, this new choice, is guaranteed to be divergence-free. So by invoking the gauge freedom in the, by invoking this extra degree freedom in the choice of the vector potential, we can always make this thing vanish. And if this divergence of the vector potential vanishes, then the equation becomes a lot simpler. And one big reason for its simplicity is the fact that this relation can be solved component by component. So each component is nothing but a Poisson equation. And we know how to solve that. The solution will be like this. Okay. So let's take an example. Suppose you have an infinite wire with the current I running down its length. In that case, the current is confined along the z-axis, and it will become a one-dimensional integral like this. And therefore, the result of the integration, as you can see from the structure of this integral, will only depend on the distance, the radial distance, which is the square of the square root of the x squared plus y squared. And evaluating this integral is pretty straightforward, except for one subtlety. If you try to do this integral naively, it will actually diverge. So what you have to do instead is to introduce some cutoff, saying that I'm going to do an integral only from minus L to L, and not directly from minus infinity to plus infinity. And that's the cutoff. So under that cutoff, the result of the integration gives you log of L over rho. But in the limit where L goes to infinity, log of L diverges. But we don't really have to bother with that, because even though this log of L diverges, it's still a constant. And when you take the curl of a constant, you get 0. So by virtue of that, we can just drop this log of L part and say that the vector potential is simply given by this term, which does not contain any log of L. Okay, and of course this expression has a perfectly well-defined limit as L goes to infinity, because L does not even show up in this expression. So now as a little piece of exercise, I want you to compute the curl of this vector potential and find out what the magnetic field looks like. And for this problem, we already know very well how the magnetic field behaves. And it will be just a matter of recovering the well-known result by being able to perform this curl operation in the cylindrical coordinates. Okay, so that's your homework.